Hello everyone and welcome to this video. So in this video we are going to talk about the concept of uncertainties, and this is one of the first videos of this playlist idea that I've come up with, which is called 1C 2Q. Let me write this here. So with 1C 2Q, what we'll be doing in each of these videos is that we'll be looking at one concept and then two questions related to that concept. So that way you'll just see something being taught, and then you'll also see that concept in action and how it's used to solve some questions. So this is the most basic video of uncertainties that we're starting with. What are uncertainties really? You can say this is the doubt associated with readings. So this is not really the error, because the error means that this is maybe something that can be removed. But uncertainties or the doubt associated with the reading, it can never actually entirely go away. If we talk about what the uncertainty would be, for example, if I'm doing a measurement of a certain quantity in an experiment, then that uncertainty would be the doubt. And again, if I think about the uncertainty, that could be the uncertainty in itself due to the instrument. And we'll be talking about this a lot in this video, plus the uncertainty with the experimental procedure, right? So for example, let's say I'm measuring some length, and let's say I'm measuring that length using a metered rule. So there is going to be some uncertainty due to the instrument, because any instrument would have some smallest reading it would be able to take, and it would not be able to take any smaller reading. For example, if I talk about a meter rule, the smallest reading it can take is 1 mm, right? And similarly, this is basically what's always going to be there. Additionally, let's say if you're taking the length of, let's say a pendulum, which is hanging from some fixed point, right? And you need to measure this length. Measuring this length would be difficult because you can't really have the meter rule exactly aligned to this, right? So you'll be eyeballing somewhat. So that would be the uncertainty due to the experiment. This you talk about a lot when you talk about your practical examinations. Right now we are more interested in this uncertainty due to the instrument. Now if I talk about the uncertainty due to an instrument, let's take the most common measurement instrument that we have in the lab, which is a meter rule. Now this is my meter rule. Again, you guys know this. If I look at any mark, let's say I zoom into here, and let's say between 3 and 4 I see 10 marks. So I know that each mark is going to be 0.1, right? 1 over 10. Now if I'm just reading off 1 point and 1 point only, so if I'm reading off, let's say, an object which is placed like this. So here what I can say is, all right, my mark could either be on either of the marks on the meter rule, right? This end could be on either of those, or it could be somewhere in between. In either case, I can eyeball to half of the smallest scale division. These readings are called spot readings if I'm just reading off at 1 point. Now, for example, this end, if I look at this, this seems like it's slightly beyond 3.3, right? But it's a little bit before. So I can say this is like 3.35 centimeters. So that's something I can say. So this end is 3.35, right? And similarly, if I talk about this end here, this is like 7.8 and 7.9, somewhere in the middle. So this would be 7.85. Yeah, this is just reading the scales. This is something you know from before as well. We are talking about uncertainties. So the idea here is this. If we are talking about spot readings, which are just a reading of one end, with spot readings, the uncertainty is half of the smallest scale division. So I'm calling this SSD, and not to be confused with the solid state drive, anything of that sort really. Also, this is not a acronym or an abbreviation which is actually encouraged by Cambridge. This is just something I write. So it's half of the smallest scale division. In this case, the smallest scale division is 0.1 centimeters, so half of that, so it's 0.05 centimeters in this context. But the idea is when I would actually try to find the length of this object, just as how I would subtract these marks to get all of this length in between. So this I'm basically calling measurements. And the idea, as we'll see in the next rule to follow, is that these uncertainties would get added up. So smaller scale division by 2 here, smaller scale division by 2 here. When both of these are added up, the uncertainty associated with measurements, that just becomes the smallest scale division, which in this case would just be 0.1 centimeters. All right. Okay. Additionally, with regards to how the questions are asked, we'll also be introducing some more quantities here, which are these. So basically, when you have any quantity, let's say this quantity is called x, it would be written like this: x naught, this is called the principal value, plus or minus the uncertainty associated with the quantity, which would be delta x. Now, for example, if I had to write down the length in this case, so that would be 7.85 minus 3.35. So I would write that as 4.5 plus or minus the uncertainty, because it's an entire measurement, that would be plus or minus 0.1, and that's how it would be written. So I'm just shifting this here to the right just so that we can see this. So these are the variables that we just talked about. This uncertainty is actually called the absolute uncertainty, AU, and based off this we'll also define some more uncertainty terms here, which are these. So if I write my absolute uncertainty as a fraction of my principal value, this is called the fractional uncertainty. So this is the fractional uncertainty. Let's call this FU. That's how this is written. And if I were to just multiply this fraction by 100, that's the percentage uncertainty. Called P. So that's delta x over x times 100 to make this into a percentage. Now what you should know regarding uncertainties is basically when you have a formula and in that formula there are a few quantities involved, how do you deal with those? So there are a couple of rules for how do you deal with those uncertainties. This is rule number 1. So this rule says that when quantities are either added or subtracted, this is an important part. So addition or subtraction, they're both dealt with in the same way, that their absolute uncertainties are added. Now something to keep in mind regarding this is going to be more evident in the following example. So this was basically the concept for today in this video, and now we'll look at some past paper questions. Now the rules related to addition and subtraction are not assessed all that much as the other rules which will come, but I've managed to pick out 2 questions. So this one is a really recent paper. This is summer, May-June 24. This is paper 1-1. And this, if I'm not wrong, is question number 6 of that paper. So this says a thermometer can be read to an accuracy of plus or minus 0.5 degrees Celsius, right? This thermometer is used to measure a temperature rise from 40 to 100. What is the percentage uncertainty in the measurement of the temperature rise? Now what this means is that when you are reading the thermometer, each reading has this associated with it. So 40 plus or minus 0.5 and 100 plus or minus 0.5. These are the 2 readings that you have. So 40 plus minus 0.5, and similarly you have another reading which is 100 plus or minus 0.5. Now if I think about it, I can also probably guess that this temperature has 1 degree Celsius as the smallest scale division, which is why the uncertainty associated with the spot readings is half of the smallest scale division, which is 0.5. But anyway, I know that when I'm going to subtract these readings for the temperature change, so that would become 100 minus 40. So my principal value, okay, let's not write delta theta here because let's just write this as T for the temperature difference. So that's going to be 60. But then associated with that change in temperature, the uncertainty, both of these were subtracted. So when quantities are either added or subtracted, the absolute uncertainties are added. So that becomes 0.5 plus 0.5, which is 1. And now to express this as a percentage, you know how to do this, which is the absolute uncertainty divided by the actual principal value times 100. So this turns out to be 1.667%, which to 2SF is 1.7%. Let's have a look at another of these questions. Relatively, this one is much older. This is summer 2010, paper 1-1, and this is also question number 6. A student finds the density of a liquid by measuring its mass and its volume. The following is a summary of his measurements. So you have mass of the empty beaker given with the principal value along with its absolute uncertainty, mass of beaker and liquid again in the same way, and the volume of the liquid. He correctly calculates the density of the liquid as this. What is the uncertainty in this value? Now you know that if you are finding the density of the liquid, what you'll need is the volume and the mass of the liquid. The volume of the liquid you already have, but the mass of the liquid you'll need to calculate from this. So beaker plus liquid minus the beaker, this is pretty obvious, that would give you the mass of the liquid. So just 70 minus 50, 70 minus 20, which is 50 grams, is the mass of the liquid. And then for the uncertainty, again, if quantities are added or subtracted, the absolute uncertainties will still be added. So this would just be 1 plus 1, which is equal to 2 grams. Now this is what this video is all about, but if you want to see how the rest of the part is done, keep watching. Now because you have the uncertainty in the mass, you will also have the uncertainty in the volume, and you know that the density is calculated by mass over volume. So the rule that we'll study in the videos to come is this, that if quantities are multiplied or divided, their percentage uncertainties are added. So I'll need to find the percentage uncertainty of the mass, percentage uncertainty of the volume, and then I'll just add both of these. So for percentage uncertainty of the mass, that's going to be the absolute uncertainty divided by the principal value multiplied by 100 plus percentage uncertainty of volume, so absolute uncertainty divided by principal value times 100, and this is how I'll do it. Because there's a times 100 with both of these, I'll just find this. So this turns out to be 10%, and when you take 10% of 5, that would turn out to be 0.5, right? So this is the percentage uncertainty. It's obviously a percentage of the principal value, so you take that percentage of this, and that's the answer you would get. Don't worry if you just kept on watching and if you didn't get what's happening in the next part, which is written in pink. I'll be going over this in the coming videos. So like this video, drop a comment if something didn't make sense, and also if you have some suggestions for the upcoming videos, let me know.